Willard Curtis. He's from the Air Force Research Laboratory, Munitions Directorate. He's the technical advisor, the Dynamic Control Sciences branch, and also the Weapons Autonomy Lead. So with any further ado, turn it over to Will.
Great. Yeah, and I'm grateful to be here, grateful for the opportunity to share some of what we've been doing. We've been looking at autonomy for a while there at Eglin Air Force Base, where we're located. So AFRL is a big team, and we're focused really on weapons technology. And autonomous weapons is kind of, I don't know, it's a sensitive area, I guess, because people are worried about Terminators, coming out of the woodwork and autonomously killing people and stuff. But, what I'll present today is, and we've thought about actually autonomy, like I said, going back to the early 2000s, and really, at least in our group there, we really think about two separate things, complementary things that have to happen. First, there has to be a perception, where the autonomous system understands what's going on in the world and the environment, all the relevant variables, and then decision making. So after it perceives, right, after it has sort of a picture in its mind about what's true, then it makes decisions about what to do. And I really want to talk about mainly today about the work we've done on the perception side, though I will caveat this. We have done a lot of work on the decision making side. How do you make robust decisions with a lot of uncertainty across teams in a way that makes sense, that's bandwidth aware and everything. So sort of, we look at technology that can be applied to lots of different scenarios, but I'm going to provide what's sort of the most common way I sell this internally in our building and across AFRL and with industry partners is the idea of how do you understand or how do you find a target in a very complex and a dynamic environment, something environment that's rapidly changing with a lot of different complex constraints. And the idea is here's maybe you're trying to find a target in a city. Which can be considered sort of a complex environment in that there's parks and there's maybe there's rivers and there's roads and there's fields and all sorts of different types of buildings. And let's suppose you're looking for like a wheeled vehicle or a tracked vehicle. The traditional way this is accomplished in the military today is to use something called the Kalman filter. Which many of you may be familiar with this, but it's basically a Bayesian estimation technique. And it's a parametric technique where you have a mean and a covariance. And those parameters basically describe your uncertainty. So those represent basically a Gaussian distribution where you say basically I have a normal bell-shaped function describes my uncertainty. So you might sort of have, so if you're a traditional estimation guy, you might have a Kalman filter that says, yeah, here's my mean, the mean location. I think on average it's probably there. And this maybe might describe the covariance matrix or describe the shape of the uncertainty, how uncertain you are about where it likely is. And so maybe if you knew exactly it was at some point it was on this street at some time moving along it, you would basically, and let's say you don't have any measurements for a while, you would basically propagate using whatever model you have of that vehicle. You'd propagate this and you have a series of Kalman filters that would sort of evolve in time, and your uncertainty would be growing at each step just because your model is not perfect, right? And you would get this at the end, so you want to say, oh, in 30 seconds, where is this vehicle likely to be? So the traditional technique would basically say, yeah, it's somewhere within this large ellipse, right? This maybe is like a 99% confidence level set. But really, if you think about it for a second, again, same picture. Here's the target. It really is probably not in an ellipse that looks like that. If it's a wheeled vehicle, it's probably on these roads. And you can see this is where it actually probably very likely is. It's on one of these roads. And if it was moving down this road, it's probably still on this road or maybe this road. So you would like a way to perceive and to represent your perceptions and your belief about where this thing likely is in a way that's richer than just sort of a mean and a covariance parameter. So that was one of the motivations. And this isn't just about tracking targets or tracking moving objects of interest in cities. This could be in undersea where you have, again, complex environments, places where it could or could not be that have very different sort of phenomenology between the ridge here and between the bottom of the ocean or the top of the ocean, or think about in complex scenes where there's mountains and there's the forests and there's swamps and there's bogs and there's roads, and again, you're trying to track vehicles or track objects of interest across different terrains. Sometimes using just a very simple but powerful method that the typical Kalman filter breaks down, and that you're not able to capture all the complexities associated with these different environments. So we wanted also, and so we started doing research on, well, how do we represent uncertainty in a way that can be more amenable to complex environments? And as we started to do this research, we found a lot of other sort of advantages to some of the things we were looking at. One is that we were able to accomplish information fusion, so taking information from a variety of different sensors. And we weren't constrained to sort of a very regular rate of information flow. So we weren't constrained to saying information has to arrive in sequence and at regular intervals, like you might expect from an automated sensor. So we have a technique that basically allows out-of-sequence information that, with unknown delays. We have an arbitrarily rich way of expressing uncertainty, so it could be, we can say, yeah, the target's likely along just these roads, or you can imagine just, if you chop this up into little bits, we could represent that. There's no, really any sort of informational cue we receive through sensors or through humans, we can represent. I don't know, most of my talk is going to be about this bullet here. We can also ingest the estimation and the perception engine can ingest very non-traditional types of perceptions. And these could even be things that humans might generate. So after we started looking at this technology for a while, we said, hey, this actually fits really nicely with some of the human-machine interface lines of research we were pursuing in another team. And the idea is that you have automated sensors. Maybe you have a collection of automated sensors. So you have radar, and you have electro-optic, you have infrared, right? You have all sorts of different sensors that are feeding you information about the battlefield. And you're trying to fuse all these things together to get a picture about what's likely true about that battlefield. So that's just the perception problem generally. But also you have human operators typically also. You might have some special ops guys, or you have friends that are walking around. They're perceiving things, they're seeing things, they're hearing things, they're smelling things. They're tasting things, they're receiving a lot of information, and they have their own perceptions about what's going on in this environment. Can you capture those things and put them together in a very strong, mathematically strong framework and represent some total perception that includes the humans and the machines? So I'll talk a little bit about that as well today. So the fundamental technology we use is a sample-based Bayesian filter. So a common filter is a Bayesian estimation engine where it's, you have some initial sort of belief about the environment, and you update that belief as you receive new information through sensors. But the trick with the common filter, which makes it so powerful, right, and sort of very useful, is that you can combine all that and say, well, I'm just going to assume that my uncertainty is distributed like a Gaussian. So my belief distribution, my probability density function is going to be a Gaussian. And so I can represent it very compactly with just a mean and a covariance. But again, the downside is, well, now you're stuck with your uncertainty at any stage of that routine, that algorithm. It's always represented as a Gaussian. So it can never represent this complex sort of perceptions that we're looking at in a more complicated battlefield. So we said, well, if you use something like this sample-based Bayesian filter, which sometimes is referred to as like a bootstrap filter or condensation filter, but most commonly it's really called the particle filter, which I like that name because it's descriptive of what it actually maybe looks like if you see it visualized. But the idea is, instead of representing your uncertainty, your probability density function as a Gaussian, you're going to represent it by a set of samples drawn from a distribution. So you can think about these particles as samples drawn from a distribution about where the target likely is. So here, maybe, right, the target, these are sort of randomly spread out through the city, meaning you think it's sort of, there's equally likely maybe that it's spread throughout. Another interpretation of these particles is that each particle is a hypothesis about where the target likely could be. And basically the idea is, instead of operating on a mean vector and covariance matrix, operating on those parameters and updating them, you're going to operate, or you're going to update the values and the locations of these particles over time. And I've mentioned several of the advantages. So we can now represent things that are much more richly and in a much more complex way than is possible with traditional techniques. So how do we do the trick of fusing soft information? When I say soft information, I'm really talking about human-generated perceptions. How do we combine human perception with perception in our Bayesian estimator? Well, so this could be voice. It could be, so it could be someone saying something. Hey, I'm looking at this street and I don't see anything. Or it could be someone saying, yeah, I'm looking at this park and I think I see a tank in the middle of it. So it could be voice. It could be text. Like maybe you receive a message from someone through some kind of interface or some other user-generated signal. But the idea is you're going to get this perception. And again, this could be voice, could be text, could be something else. And you're going to need to basically turn that, whatever that thing is, through some function into a likelihood function. The likelihood function sort of is related to this probability density function, but it basically provides how much can you trust this measurement. What is that? How should your belief be modified once you receive this human report? And this is really, if you look at this, how Bayesian fusion, again, is the engine, just like with traditional estimation techniques. And Bayesian fusion is going to start with some kind of prior belief distribution. And it's going to be updated by likelihood updates every time you receive a measurement. So this process is exactly the same whether it's human or machine. A machine sort of, so think about an automated sensor like a radar, right? You take that off as it's manufactured and you characterize it immediately, right? You run a bunch of tests so you know the errors associated with that. And you basically build, hey, I know if this machine reports or the sensor reports something, how to turn that into a likelihood function because you characterize the errors. So you have to do the exact same thing with humans. So how do you do this? And the state of the art, even if you look at people trying to fuse human-machine perceptions, it really is a tricky thing because there's a lot of things going on with humans when they tell you something, even just like in real life, right? Your wife tells you something, you're like, well, how much do I trust this, right? Because, how fatigued are they? How alert? How stressed? What time of the day is it? Have they eaten recently? All these things, how trained are they? So there's lots of things that affect our human perceptions and affect the things we communicate as humans, how we describe those things that might alter. So maybe if someone says, yeah, I see it. I'm almost sure I see it along the street. But what does that mean? Is that 99% sure? Is that 90% sure? Is that 85% sure? It probably depends on the person, right? It depends on how angry they are, how sleepy, all this stuff. So it's tricky to model all these things. But I'll show you how we've tackled it. We basically say, okay, you're going to observe something. So the human's going to maybe see something or hear something. And then there's biochemical, there's always, you think about the whole biology of the person as a filter, as a mathematical function that's going to alter that actual perception, that observation, and turn it into some kind of perception that he's going to again communicate through voice or through text or through some other thing. So we basically try to model each step of this from the observation to the perception to the measurement. And then the measurement, the way we're incorporating it is via touch. So someone who's sort of manning the perception engine. He's getting all these reports, voice, text, or whatever. And basically, it's his job to, with his finger, to swipe out. And basically, you can imagine having a map of the battlefield. And on that map is displayed like this particle filter. And I'll show you maybe some alternate ways. We actually use a heat map now to represent uncertainty. So maybe this is a picture of the battlefield. This displays, so what you're seeing is like the density of the particles. If there's high density, it's red. If it's low density, it's blue. So there might not be any particles in this dark blue region. There's quite a few particles in these redder regions. But the idea is there's a human manning this station or this tablet or their screen, and he's seeing all the fused information from all the sensors and all the people. And if he gets a new report from a human, he basically, again, looks at this map and says, okay, this human is reporting a perception, an observation, a measurement about some part of this battlefield. And he basically runs his finger to indicate whether is the target more likely or less likely to be in a certain region. So he basically has two modes of interaction. He can do a negative mode where it's like, hey, the human has told me it's not here or not likely to be here. And basically he's going to shade out and de-weight particles in some region associated with that perception. Or alternatively, he could do the opposite. Someone might say, yeah, I think I see it. It's near the military base over there. And again, he could use his finger to turn that verbal statement into a likelihood function, basically. So we've done a lot of research, and there's lots of different ways you can sort of enhance the richness of this touch interface. So one way is, again, it's the trick of like, well, how do you encode confidence, or how do you really turn that verbal statement into something, into a likelihood function? So one of the ways we have is basically, if you ever, like way back in the day, Windows 95, they had this program where you could draw. They had like a spray can where you'd spray out, it would sputter a bunch of particles on. You remember this thing? Okay. So it's kind of like that. As you run your finger across the tablet, it's sputtering out a bunch of particles, which you can see in this picture. So maybe this is like a finger swipe. He's touched this tablet, and the harder you press, the more sputter happens, right? The more particles are thrown out. And then we basically use a kernel smoother to smooth over that, and that turns basically a finger swipe into a smooth function, into this. So you can think about this as now we've turned that, we've gone from observation to perception to measurement through the touch interface into this is now a likelihood function that will be fused via Bayes' rule with your prior belief. And that's basically our current technique for doing this. We've added a few bells and whistles, and it's because this is fundamentally two-dimensional, right? What if you were trying to track a target and it's important the direction it's heading or the direction it's moving? Well, now you're talking 3, 4, 5-dimensional space if you have add all that stuff up. So we've also looked at maybe the direction that you swipe could indicate the direction the target's moving, for example, and a few other bells and whistles. But this is basically it. And the idea is that it's a flexible and natural way. So humans are good at sort of finger painting, right? Which is what this turns into. You got this thing, you're seeing all the information displayed. So you've got this nice color heat map that's showing where things what's likely to be true about the battlefield. And then as you receive new verbal reports from your soft information sensors, that can be ingested or put into the filter via touch. So in the interest of time, I'm going to skip ahead a little bit here. I'm going to talk about this. So going back to the fundamental problem of incorporating the human side into what's fundamentally this mathematical framework where you're doing Bayesian fusion. The trick, again, is turning those human perceptions, which are biochemical signals basically inside someone's brain, into this mathematical likelihood function. So what we wanted is a way to, so I don't know if you can read this, but this says alertness, this says heart rate, this is galvanic skin response, stress, training. And we wanted to build a relatively sophisticated yet simple model of how the different physiological factors and different human factors like training would modify the confidence we associate with a certain human soft sensors impact on the filter. So this idea of this total competence will be like a global weight that's applied. So that if the human basically maybe puts in something or says something, how much weight just in terms of like a global factor do you assign to that in terms of how much can you trust it? And the idea is, so like for example, if the heart rate is elevated, maybe that implies that that individual is stressed out. And there's a curve associated with stress. If you're under stressed, it's likely that you're not performing optimally, right? And if you're overstressed, of course, you're not performing out. But if you're like sort of medium stressed, it's like usually that's when people are like on point and very focused. But that's the idea. Or for example, alertness. You want someone to be alert. So maybe if their heart rate is too low, you're maybe not as alert, not as likely to see things. So if they say, hey, I don't see something here, well, do they really not see it? Or are they just not looking because they're not very alert? The idea was, let's build and this is basically a Bayesian belief network. So again, these are all random variables, so we don't really know exactly their stress level or their alertness level, for example, or their training. But we can basically model this probabilistically, and basically be able to give some measure of some way of estimating, hey, how much should we trust what this person's saying? So we partner with Army Research Lab. They have a human factors group that has a lot of experience sort of measuring physiological signals. So they have a cap also where they can measure EEG and all these other sensors, eye trackers and galvanic skin response and all this stuff, heart rate monitors, to try to get a picture. The problem we ran into, so I guess I'll say the shortfall we're at, we kind of hit a wall in that in order to sort of train this, in order to sort of understand what all these connections are, what all these conditional probabilities will be, requires a lot of tests. You got to get a lot of raw data about actual humans, and it's very variable, human to human. And I'll show some slides to highlight that in a second. So it's a tricky problem, and then it's really at the end of the day. Let's say you got 1,000 people, and you ran them through this target tracking problem for a while, and you looked at what they were putting in and versus truth after the fact, and you tried to do some kind of machine learning or whatever to say, hey, what do these edges really look like? Even then, you wouldn't know, well, is this model only true for that specific thing that you did the experiment on, that specific application, whatever you trained, whatever you collected the data on, or does it generalize? And we weren't even sure, and the literature is very sparse. We weren't even sure what are the right nodes to include here. Is stress and alertness, are those the key drivers or something else? And actually maybe uncharitably, I would say there's not a lot of science really looking at this. There's a lot of human sort of research literature looking on, hey, but it's hard to pin down into a framework as quantitative as what we're looking for. So that's still sort of an area of interest that we're looking at. Here's what we did do with the Army was a simpler problem. This is the idea of, so it's the RSVP, which stands for Rapid Serial Visual Presentation. You have a human, and you're rapidly presenting that human with images, so like 5 images every second. He's seeing these images, and he's basically going to hit a button if he thinks he sees something of interest. So maybe he's looking for a specific thing, like a chair or a tank or a person with a gun or something like that. So he's seeing a bunch of images, and he hits a button if he thinks he sees something. And we wanted to use our Bayesian framework in this. And so the idea is you take prior knowledge. So again, you have a prior. Hey, prior intelligence says you're probably not likely to see any threats today, or any objects of interest today. And then the human says something again, or gives a report. He says, hey, I don't, he doesn't hit the button. I don't see a threat. And basically, we fuse these things. Again, we have a simple model where we fuse these things. We look at these different physiological signals, and the output of which is basically a distribution. Again, some kind of function that says, hey, what's the probability now, given that he said that, given all of his physiological signals, and given this prior, that he did or did not see something. We did a bunch of tests, and we had automated image processing algorithms also. Again, looking at these images, and this is basically just, support vector machine and some other sort of machine learning type approaches that we're doing a classification, right? Classifying, hey, is there an object of interest in this image or not? So we had a comparison, human and machine. But I want to talk just about the humans for a second. These are, so what you're looking at, these curves, these are receiver operator curves. So just a measure of sort of the effectiveness of these humans as detectors, is whether they are doing a good job detecting whether there was an object of interest or not. If a random detector, just a detector that actually provides no benefit at all, is this red line. That just says that the detector is just guessing, it's flipping a coin. The ideal detector would be like a curve that just went like this, just across the upper, this vertical piece here, and this right here, and the horizontal piece here, right? It would be just like that. So the further this curve bends up like that, the better. You can see I guess what I'm trying to emphasize is there's great variability across the people. Really, it's not enough to say, to build a model for, hey, how do we fuse humans with machines? What's the magical number that says here's the factor which turns a human observation into a likelihood function? Because it's different for every human. Right? And of course, I think if you did this, maybe, and I don't know because we didn't do enough experiments. I think it likely that the best humans are probably going to be best across different days and at different times, right? I don't know that for sure, but I'm saying that. So it's likely, but also it probably does vary day to day, time to time. When was the last time you ate? Did you have an argument with your wife last night? All that probably affects these curves when you think about it. So it's a tricky problem, and one of the things we've batted this idea around is can you provide like a file that goes with the human, and basically every once in a while you test that human, right? You do some kind of the calibration routine on the human to say how good are they. That way, as they're interacting with the autonomy, you have some concept of how much you should trust them or how much you should sort of await the things that they do in terms of allowing it to influence the belief of the filter. Here's again, a wide variation in human performance. This is the button press, how good they were at basically pressing the button when they actually saw something. Again, you see huge variation between the humans in terms of their performance. So I wanted to talk just a minute, and there's been, I guess, quite a bit of discussion already about the importance of dealing with information or dealing with delays and time lags in the system. This is something that we struggle with as well, because as soon as you have humans that are an integral part of your perception engine, you get delays because humans, they had to do something first and they get back and they give you a delay, and so maybe the report or the radio doesn't work or something, and they have to change frequency, and so you get a delayed report. But it's still very valuable information, especially the human maybe calls in and says, yeah, I just remembered. 2 minutes ago, I saw the target. It was right next to the church over there on this street, right? So it's very valuable information, but how do you fuse it when it's old, when it's very stale? So basically we developed, a fast way to fuse information that arrives out of sequence. And the costs, so nothing's free, right? The cost was, you now have to, instead of sort of keeping this list of particles, this list of samples, where they're at and their likelihoods, you have to save for each particle a trajectory, like a history of where it was in the past. And the further in the past you go, of course, the more able you are to sort of retrieve and fuse out of even more stale information. So, for example, maybe for each particle you store a history of its trajectory over the past 5 minutes. Well, that gives you the power to fuse out-of-sequence measurements up to 5 minutes, right? But if you get a measurement that's from 6 minutes, you don't have any memory of the filter at that point in time, so you can't feel. So that's the trade-off, right? So the more memory you allocate by storing longer and longer histories per particle, the further back you're able to go in terms of fusing those out-of-sequence things. I'm running out of time, so I'm not going to go into the ones and zeros here, but we basically, there's a way to do this brute force that's very, very slow, and there's a very fast way, and that's what we've basically showed. That the fast way is much faster, and also it gives equivalent performance. So what are we doing now? So this has been going on for 5 or 6 years, and I guess I should have mentioned at the start, this is a team effort. This is not just me, but Emily Doucette and a series of graduate and postdoctoral researchers over the years have all contributed to this. Where we're at now is we're trying to combine this idea of a Bayesian belief network. It models a human, but it also models a lot of environmental variables that are not typically taken into account. So the threat state of the world, things like do you believe the target's on the land or on the sea? Is it mounted in a vehicle or is it on foot? Contextual sort of information that humans are very good at processing and using to find things or to do things, which are typically not represented on the autonomy side. And we think by adding this level of contextual awareness through some Bayesian belief network, we have a much more powerful perception engine that captures context as well as the details about where something likely is through the particle filter. I don't have time to talk about this today. How many minutes do I have? 2 minutes. Okay. We did a series of experiments with Army Research Lab, and the idea here is we're trying to do a decision aid. So the idea is you have a commander that's basically going to control fire over some region of the battlefield. He's trying to decide when to fire a weapon and where to fire. And he's collecting information. He's got some automated sensors. Maybe he's got like some unattended ground sensors that give you vibrational cues about, yeah, something just passed here. He's also got some human sensors. He's got people, operatives in the field that are making an observation. But again, at the end, he's got to make this life and death decision about, well, I'm going to fire a 500-pound weapon. Where do I fire and when do I fire? So basically what we did is we used our particle filter technology to provide like a heat map representation where the target likely is. And as well, we said, hey, but also when you fire, that weapon's going to fly out with some uncertain trajectory. It's going to be influenced by wind and other factors. And all this can be rolled up into sense. So if you actually say, I want to fire here, well, where will it actually land? Well, that's some function, right? And then there's also collateral damage. There's these, schools and hospitals, maybe things you do not want to destroy. And they have varying levels of sort of badness, right? So maybe it's like the worst case scenario is the kindergarten. You absolutely do not want to hit that. But there's also maybe this, there's a university there as well. That's also pretty bad, but not as bad as a something like that. That's the idea. So basically, you're able to weight a priori. You weight these different risks associated with firing. And of course, the biggest risk of all might be like you don't hit the target. You really got to hit that target at the end of the day. So the idea is, I don't know I hope this works. I've got a video somewhere. So yeah, here's a sort of maybe a picture of it all working. So you see, these are special ops guys that make observations. This heat map describes where the target likely is. Again, you get every once in a while a sensor sees it, so you start to get a belief about, hey, this is where it could be or as likely is. And here you see it's rolling together all information about the wind, about the uncertainty of the firing, about the collateral damage, about this belief about where it is. It rolls all that together into a fused sort of decision aid that tells the commander when to fire. So you see at the bottom here, this is telling it when to fire. This is like a low confidence, yeah, don't fire now. And it tells you actually fire not recommended. Then as your information gets better, you become more certain about where it is. It'll jump up and say, yeah, fire now, dude, idiot, fire, dude, you've got a perfect thing. And it's like, so the idea is this is looking at the Bayesian risk of making a certain decision. And it does this calculation for every point in this field. And you point at, and it basically says, hey, at the lowest risk point, the best possible thing, what's the risk? What is your expected loss if you make that? And if the expected loss is low enough, it says, yeah, fire now, right? It makes this decision. The idea is it rolls up all the uncertainties together, something that the humans find difficult to do, taking all this information and mathematically calculating what are the odds of all these different things and what are the expected payoffs of all these different things, and provides an interface basically to help an operator do that better. So, do I have a minute? No. Okay. We have a bunch of other cool stuff we're doing, but I'm gonna stop there and take any questions if you have them. Thanks.